Good morning. We have the Doppler effect, and we'll try to do the Doppler effect in less than 10 minutes, 2 hours of class time with exercises. So, the Doppler effect. You know about the Doppler effect. It's when an ambulance arrives, approaches you, a motorbike approaches you, or a car, and there's a perceived shift in frequency of the signal. So as it approaches and then goes past, it goes so basically the pitch changes, and we have to look at why that is. Okay, so it's when there's a change in pitch as heard by an observer or a detector. When the source of sound is moving relative to the medium and the observer, which is usually what happens, or sometimes the observer is moving relative to the medium. Most of the experiences that you have are the first one, or it could be both. There's a shift in the observed frequency according to the observer, which depends on the speed concerned. We have to do calculations for 1 and 2, but not for 3. Okay, here we do. One way of looking at this is to look at wavefronts, and we'll click on this. So what's happening is the ambulances are arriving and coming towards the observer. It's sending a pulse every, or a certain frequency, every second or so, and observe what happens to the wavefronts as the source approaches the observer, and when the source recedes from the observer. So start again. Now, you notice that the wavelength here, these wavefronts are very much bunched together. They hear tick, 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 tick. Then afterwards, they hear a frequency which goes tick, tick, tick. So effectively, on approach, they hear a high frequency because the wavefronts are bunched up. Apparently, the apparent wavelength gets shorter. And then when the source recedes, the frequency goes down, and the wavefronts get much more spaced apart. So that's basically what we need to look at. So we've done that. So here we have a stationary source. We have an observer here that is able to observe the same frequency, click, 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 at the same frequency that was emitted from the source. These wavefronts propagate in all directions symmetrically to the source because the source is stationary. This is not the Doppler effect. However, if the source is moving in the medium, in the direction that it's moving, the wavefronts are bunched together. Behind, they're spaced apart. So the source is moving basically to the right. The center of each new wavefront is basically started in a position which is slightly to the right. So effectively, we end up bunching up the wavefronts on the right here. On the right, the distance between the wavefronts is shorter. On the left, it's further apart. What about the observed frequency? The frequency observed here is high as it approaches, and the frequency observed here as it recedes is low. And this is another way of looking at it. The source is moving to the left. Here we have a perceived smaller wavelength. Here we have a perceived larger wavelength with respect to the medium and the observer, but not the source. Now, what happens if the source is moving with a source which is the same speed as a wave? Basically, the wave gets so bunched up that the wavelength becomes nothing, becomes zero. So it means that an observer here doesn't observe the signal from the source until it passes. Then you get basically a point here where all the signal arrives at the same time. So you get like a bang effect, and this is called called breaking the sound barrier. For example, they hear all the sound from the last few seconds at the same time. So they observe nothing until it arrives, and you hear this big shock, this big pressure wave, this big bang, or thump, as this wall of pressure goes by. Okay, the equations are this. This is the equation we need. This is taken from the data booklet. F1, F prime is the observed frequency by the observer. F is the frequency of the source. V is the velocity of sound, and U is the velocity of the source. Now this can be plus or minus depending on whether it's approaching or receding. Now, against probably your intuition, when it's approaching, you use the negative value, because basically you're going to be divided by a small value here to get a small denominator, so this will be a larger frequency, a higher frequency when it's approaching. And when it's receding, you're going to have we use the addition sign here. So you're dividing by a larger number, so the observed frequency will be smaller. Here's an example. A car is travelling at 30 meters a second, emits a frequency of 200 hertz. You have to find the observed frequency. Pause and you do the problem. Then try the same for a jet, which is travelling at 260 meters a second with this same frequency. These are the answers. Okay, this is 220 is the approaching frequency, that's the receding frequency. Approaching frequency, receding frequency. On the other hand, if we have a moving observer, we use this formula. This is the observed frequency, this is the frequency from the source, and U naught is the speed of the observer. V is the speed of the signal, the sound. And here we have another problem which I would like you to do. So pause and try that problem. These are the answers. The unit should be there, of course, hertz. Solve problems on the Doppler effect for electromagnetic waves. We use this value, delta F, which is a shifting frequency, is V divided by C times by F. This only works when the velocity is much smaller, less than 10% of C. Then it's going to be slightly different. Yes, thank you. Okay, back to that. If we have a problem, let's say that a frequency is emitted at 890 megahertz, the velocity of the source is 100 meters a second, the speed of light is 3 times 10 to the 8 meters a second. What would be the shift in frequency if this body is moving towards you at 100 meters a second? And it will be 297 hertz. So try to put that into the formula and work that one out. We have some problems I would like you to do. So pause here and try to do these problems. Outline an example in which the Doppler effect is used to measure speed. We have a radar here. That's used to measure speed. It sends a signal to the approaching car, then it's reflected. What happens here, by the way, is the Doppler effect is doubled, because not only is it you have a stationary source and a moving object, a moving observer, but then it's reflected, and this new then you have to apply the Doppler effect again, because the new source, the object that's moving, is treated as a new source, so it happens twice. Once is the original signal, one is the reflection. So this equation here would be double the frequency, so it would be 2 lots of this value if it gets reflected. Do we have some problems here? Try to do this problem. Pause. Try this problem. Notice that the source is very close to the path. Pause. Similar question. Notice that the observer is quite a distance from the path of the source. Pause. Okay, try to do this one. Pause. Try to do this one. Pause. Try to do this one. Notice that they're not in the same line here. Pause. And I think we've just seen this one. Pause. Try this one. Pause. Another one. Pause. Here again. Pause. Here again. Pause. Same again. Pause. Same again. Pause. This is an excellent question. So try to do this one. It appears that there are no correct answers, but there is a correct answer. Pause. That's it. Okay.